This Explain Everything video is intended as an instructional resource to help teachers more effectively conduct a lesson as described in the teacher notes in this unit. The same acceptable use policy restrictions apply to this video as they do to the rest of the curricular materials made available by AMTA. Beginning chemistry students find it difficult to distinguish between a formula unit like CaCO3, which describes the empirical formula of an ionic solid, and a molecular formula like NH3, which describes discrete molecules. The activity described in the September 2009 issue of the Science Teacher has students examine the crystal structures of three types of solids so that they can devise rules for distinguishing atomic, molecular, and ionic substances. This article, found in the resources folder for Unit 6, relied on Mercury software, which is available from the Cambridge Crystallographic Data Center. At this site, one can download a free version of the software for Windows, Linux, and Mac operating systems. The document Using Mercury in the Unit 6 Resources folder gives detailed instructions for downloading, installing, and configuring the software. This Explain Everything project provides further guidance in the use of Mercury. This is the default window you see when you first launch Mercury software. The first step is to change the view from wireframe to ball and stick. The second step is to check the packing box in the lower left-hand corner. The third step is to deselect the Show Cell Axes box in the lower right. The image you obtain for carbon in the form of graphite doesn't appear very helpful at first. However, if you click and drag a corner of the window, you can rotate the view. This view shows that the carbon atoms form parallel sheets of hexagonal rings. Students might incorrectly conclude that each of these three sheets is a molecule with many carbon atoms. One way to convince them otherwise is to change the A, B, and C packing parameters from the default value of 0 to -1. This has the effect of expanding the view, so to speak. Students can see that the sheets extend indefinitely. Be sure to return these values to 0 before opening the next crystal structure. When students open the file for dry ice, they can see that it consists of individual molecules of carbon dioxide. By contrast, Mercury's representation of calcium carbonate shows a regular lattice of calcium and carbonate ions that are interconnected. There are no discrete molecules of calcium carbonate. While Mercury software works for classrooms with access to computers, it's not helpful for those teachers who work with Chromebooks or tablets. Adam Smith Classroom is a web-based application which provides an alternative to Mercury. Adam Smith Classroom is a reasonably priced, subscription-based application with many resources that a modeling chemistry teacher could use. Teachers can request a 2-week free trial at the website. The feature that is useful for this activity is the molecule library. This folder in the molecule library contains the structures called for in the activity. One simply selects the desired solid and then clicks on Load Selected Model. David Doherty, creator of Adam Smith, customized the molecule library to provide a subset of molecules specifically geared for this activity. As was the case with Mercury software, the representation of the simplest unit cell doesn't always provide enough information for students to determine to which category the solid belongs. In this image, carbon in the form of graphite is displayed. Fortunately, the app allows the user to adjust the crystal lattice parameters to reveal more of the structure. When this is done, one can see that graphite consists of parallel sheets of hexagonal arrays of carbon atoms, making it an atomic solid. The view of crystalline sulfur clearly shows the puckered rings of S8 molecules. One key difference between Mercury and Adam Smith is that while the latter shows the covalent bonds between carbon and oxygen atoms in the carbonate ions, it does not show connections between the calcium and carbonate ions like you see in Mercury. The third option is to use the HyperDoc developed by modeler Melanie Bunda, which makes use of MolView, a crystallography viewing platform similar to Mercury. The tiny URL at the top of the screen takes you to the Google Doc, which has embedded links to the solids examined in the activity. Here is the representation of the unit cell for graphite that MolView provides. As with Mercury and Adam Smith, it is necessary to expand the view in order to discern what type of solid graphite is. This can be done by choosing Load 2x2x2 supercell from the Model menu. Doing so provides a view of the structure of graphite similar to that shown in Mercury and Adam Smith. Like Mercury, MolView shows connections between the calcium and carbonate ions in the ionic compound calcium carbonate. While MolView is free, it does not open existing CIFs like Mercury. Instead, one has to enter the name of the desired substance into the search field, choose one of the databases, and hope you obtain a structure you can work with. For example, in the case of sucrose, not all of the models that MolView loads allows you to expand the view. Still, the links provided in this Google Sheet point to models that will work well enough for the purpose of this activity.